Okay, we've talked about calculating the AIC and evaluating which model we like based on the model that has the lowest AIC value. But in fact, with AIC, we can go a little bit farther than that, because we can actually evaluate within the set of models how good models are relative to each other. It's actually the relative AIC that we're interested in. So we're going to call that delta sub I, and that's going to be equal to the AIC of the ith model minus the AIC of the best model, or the minimum AIC, from that model set. Recall, this is always going to be relative to the particular set of models that we've got. One of them will have the lowest AIC, and now what we're asking is how far away are the other ones relative to that best one. So we can have a look here now at the full set. We've got our 5 models, our AIC values, which go all the way down, and our K values, which is the number of parameters that we've got. And now what we've got is another column, which is the delta AIC, which is the distance between the best model and the particular model you're interested in. Given this particular pattern, then, the AIC best model has a delta of 0 because it's the value of the AIC minus itself, and then each of the other ones is ranged away from that. So the second best model is a AIC 3.3 AIC units away, the third best is 6 units away, and so on. So what are we going to do with this delta AIC model? Clearly it still gives us a ranking, so we haven't really moved anywhere particular from the observation of the order of the raw AICs. If you recall, we base the AIC on the log likelihood, the likelihood of the parameters given the data and the model. Well, it turns out that given the AIC, we can actually calculate the likelihood of the model G being the correct model given our data. And that expression ends up looking something like this. So the likelihood of the model G sub I given our data is proportional to the exp, the e to the power minus 1/2 of the delta i's. So the larger the delta I is, because this is a declining exponential function or a negative exponential function, the larger the delta I, the lower the likelihood of the model G given the data. And we can take this likelihood of the model relative to the other models in a set and calculate the relative evidence for the model simply by normalizing this likelihood relative to the likelihood of all of the models in a set. And we're going to call that W for the weight of evidence, or the AIC weights. So what we've got is W is equal to that likelihood expression that I just showed you divided by the sum of the likelihood expression over all of the models in the set. And if we do that now for our fifth order models, what we get is a new column W that now has the weight of evidence in favor of a particular model. And so what we can see is that our AIC best model has 80% of the evidence, the second best model has 16% of the evidence, and the others are correspondingly lower. A few key points that we want you to recall about this model selection using AIC. The key improvement over many other forms of model selection is that it allows us to accommodate model selection uncertainty. So the most important thing to remember is all of these estimates, all of these quantities, even the AIC value itself, are statistical estimates, which means we're not certain about those values. They are estimators. So it means that even though we've picked one model as the best model, other models may also have some probability of being a better model, even though in this particular instance they haven't turned out that way. We can accommodate that uncertainty using what's called multi-model inference, which I'll cover in another topic, and by calculating what's called the unconditional sampling variance. Within the set, the models can vary. So we can calculate AIC for different models, but the data that we are calculating the AICs from must be fixed. If we are going to compare different models, we have to be comparing models that have been fit to exactly the same data set. Finally, this is not a test of these models, it's a ranking of these models, a relative ranking of how good they are at approximating the unknown truth. And that's a ranking that's relative only to other models in the set. Okay? So you could still be in a situation in which your best model within the set is absolutely a bad model. That's why you need to do the model checking exercises. Okay? But you might still find that within a set that you tested, it's doing better than any other model. Okay, so there's an important distinction here to be made between relative quality of a model, which is what AIC and the AIC table is testing, and the absolute quality of the model, which is what you're checking when you look at the fits of the residuals and test the assumptions of your model.